So good morning, everyone, and thank you so much for joining us for this seminar. We are really very happy and proud to welcome today HENS. Several of you may know him because of his role during this COVID-19 pandemic in Belgium, especially as member of this GEES group, which was the main advisor to the Prime Minister until recently. But I would say that today we welcome Niels as a scientist, as a professor in biostatistics, both at the University of Hasselt and the University of Antwerpen. I say as a scientist, really Niels is a top researcher in the field of biostatistics and modelization of infectious disorders. He's a top researcher, and as just one demonstration of this, is the recipient of a consolidated grant of the European Research Council. So I will not be very long in this introduction. I'm sure that Niels has a number of important things to tell us, and especially I hope that during this seminar we will learn how modelization can help us to understand and policymakers to take the right decision in these difficult times of uncertainty. I would like to add that Niels was invited by Mathias de Watripon, who is the co-director of the Institute, and Mathias will join us very recently. He was just invited unexpectedly to attend a very important meeting of the Walloon government, but he should be with us very soon. Niels, the floor is yours, and thank you again for being with us.
Okay. Thank you, Michel, and thank you also to Mathias and also to Anna for all the practical arrangements. I'm very happy that I can share some of the work we've done during this crisis with you. And yeah, there are many collaborators here, not only within Belgium, but also worldwide, I would say. We've been exploiting the network, let's say, within this crisis. And I also want to especially thank Marius Gilbert, who contributed to this presentation, and we exchanged slides basically, and so some of the slides are his. I would like to start and with Daniel Bernoulli. And why do I start with Daniel Bernoulli? Daniel Bernoulli is actually often claimed to be the first person who developed a mathematical model for infectious diseases. And he looked at smallpox and inoculation to eradicate smallpox. And the point that he made was actually that it was good for the population to start inoculating people with cowpox, because it has been shown that cowpox was indeed able to prevent smallpox from happening. Now, Daniel Bernoulli used a mathematical model for doing so, and he actually used what we would write nowadays as two differential equations. And the way he worked was he actually, using these differential equations, resembled what was going on at that time. And then he mimicked, by changing these differential equations, what it would mean that if smallpox would be eradicated from the population. And he at that time showed that the median life expectancy would increase with 10 years. So there would be an enormous effect of an eradication of smallpox from the population. Now, he entered into a lot of discussions with Jean-Laurent d'Alembert. And actually, looking back at that and looking at the literature, both Jean-Laurent d'Alembert and Daniel Bernoulli were in favor of vaccination or inoculation at that time. But Jean-Laurent d'Alembert made a very important point, amongst other points. He made a very important point that, yeah, this was a conflict between individual choices and what is best for the population at large. And especially because cowpox inoculation was not without risk. There was substantial mortality associated to it. And so it was really about balancing individual and population risks against each other. And I think this is a topic, and that's why I touch upon it, that is very much issue nowadays. Of course, this is the story here is about inoculation, but much more. This topic is very relevant today because it's not only inoculation, but it's also in terms of individual risk and so on, compared to the population being at risk. And just as a side note, but actually quite important as well, is that Daniel Bernoulli could be regarded as one of the first persons to introduce competing risks analysis. We would frame it a little bit differently today. And also Jean-Laurent d'Alembert worked on that topic, competing risks, but with other methods than Daniel Bernoulli did. And likewise, in infectious disease epidemiology, a lot of people have contributed with a lot of very innovative ideas that we still use today. And I think about the EM algorithm, which McKendrick actually introduced in 1926, and which is very much an important issue in infectious disease epidemiology, in the fact that we do not observe all the things that we want to observe. There are, statuses, infectious disease status, and I'll come back to that in a moment, that we do not observe given the data that we have at our disposal. And so we have to find clever ways of making the most of the data that we do have to infer what is not well known to us using, for instance, an EM algorithm or, and nowadays, Monte Carlo methods to do so. In 1956, Bartlett actually introduced chance events to the problem, let's say, of infectious disease epidemiology, acknowledging that that there are indeed chance events that underlie the transmission of a pathogen. And of course, there have been many seminal contributions since, and I'm only mentioning the monographs by Bailey and Anderson and May, but there are many more. This is a picture I'd always like to show to explain a bit better what I've just indicated as being the things that we want to know and the things that we observe, and how to infer one from the other. So this is a picture taken from the book by Keating and Pesciolani. And what is important to notice within this picture is that we have a time axis, and this is really representing the course of a disease in one individual. So we all have our immune system with very general immune mechanisms that fight all pathogens, let's say, but are not specific enough to prevent pathogens from invading our body and from multiplying within our body. But then at a certain point, when a pathogen invades, we have a time of infection. And then the idea of a virus, for instance, is to replicate itself. And once that virus starts replicating, at a certain point, the immune system hopefully conquers the virus, and that replication is stopped, and the pathogen will actually finally be eradicated from the body. Of course, this is not for all pathogens in the same way. And so there are many versions of this diagram to make. And but the idea here is especially showing some principles that are very important within this in this SARS-CoV-2 pandemic. Small remark is, of course, our immune system will recover. It will, after being deployed, it will actually retract as well to be ready to fight the next intruder. But it also will remain elevated to some extent. And that could mean different things by humoral immunity components, or that could be cellular immunity components. And for SARS-CoV-2, I believe that's not that well understood yet, although a lot of significant advances have been made in understanding that. Now, what is important for us here in my seminar here is, well, the infection status. So if we consider this to be the infection status, so people are susceptible before they're infected, then they are infected, but then at first instance, they cannot transmit the virus to others, for instance, and they're called exposed or latently infected. And after a while, they will have enough of the pathogen within them to actually share with others, as you can say, and they will be infectious. And after in the infectious period, they will recover, hopefully, And yeah, then depending on which virus you're working with, you're looking at, for instance, if we think about SARS-CoV-2, it is likely so that from recovery, people turn susceptible again, and so on. And actually, that's a layer, these infection statuses, that's a layer that we can model quite well, mathematically speaking. Some models will be much more complicated than other models. And yes, we can have a lot of discussions about how to do it in the most optimal way. But in principle, in general, we can do this fairly well, as long as we know what is at stake and what is the question we want to answer. We will use different models for doing so. What is much more difficult, however, is to line up the model that we've developed, the conceptual model that is developed with data. And the issue there is that often enough, we only know the medical status of individuals, but also knowing that medical status is very limited. And think about period in which people are diseased. Well, not all people have the same amount of symptoms, think especially on COVID-19. So you have people without symptoms, you have people with mild symptoms, and you have people with severe symptoms that need to be hospitalized, taken into intensive care, and some people also die from COVID-19. So we do not observe all of that, and especially also because health-seeking behavior in individuals is very different and very heterogeneous. So it's quite complicated to grasp that very well. And with mathematical models, however, we do try to do that so that we can learn and to investigate what are the most clever ways, basically, of dealing with this virus. What is very important as well is the incubation period over here, the time between the time of infection and the time of symptom onset. And this incubation period is a period in which, well, people are already infected with the virus. And for SARS-CoV-2, very importantly, also able to transmit the virus to others, but they don't know yet that they have been infected. And in a moment, I will share with you the first analyses that we've done in February, where we tried to investigate how this all evolved and also try to look at whether or not there was pre-symptomatic transmission and what the extent of pre-symptomatic transmission really was. The overlap between the incubation period and the infections period is a very important ingredient here. And it's also the main difference between SARS-CoV-1, MERS-CoV, and the SARS-CoV-2 virus. So SARS-CoV-1 as well as MERS have been believed only to be able to be spread to others when people were already showing symptoms. And we know for SARS-CoV-2 that that's not the case. And that is why SARS-CoV-2 exhibits these properties that enable it to be really a pandemic. A very important property for such a virus to have, to be able to become a pandemic virus. If I look at this picture, then of course we can think about further along these lines of what are the infectious disease data that we should look at. And a lot is observed, and what has been communicated on a daily basis in all the media is the number of confirmed cases, number of hospitalizations, the number of deaths. And we can discuss a lot about the way these things are reported, but essentially this is what has been reported, and lately also what is called the seropositivity rate has been reported as one of the more important data sources. All of those are prone to issues. There are many issues, reporting issues to deal with, and so on. So it's also very important to take them with a grain of salt, to interpret them in the right way. And what I think is often underused, for instance, is the use of serological data, although it has its limitations, especially for SARS-CoV-2, but also other tools like surveillance data. And in Antwerp, we developed a large corona survey, an idea by Philip Bertels, where we looked at questioning people about their behavior, about their perception on this pandemic, and so on. And I should have updated deadline. We are developing infectieradar.be in the different languages of the country, also in English, where we will actually ask people to participate to report on their symptoms and how they dealt with, for instance, quarantine, isolation, and so on. This will be launched now in October. The survey questionnaires have been finalized, and it's actually undergoing deployment right now, and we will be communicating about that. What is the goal of Infectieradar? It's actually an initiative as part of the European Horizon 2020 grant I'm coordinating with the London School of Hygiene and Tropical Medicine, with RIVM, with the ISI Foundation, with the University of Bern. And the idea here is that we do this in Italy, in the Netherlands, in the UK. They've already adapted the Great Influenza Survey to do this as another source of data, so that we can ask them also about their behavior, but also for the health economic evaluation. This will be a tool to investigate or to get more information about the quality of adjusted life years and so on. So a new data tool, a tool to gather more information, and maybe also in the future to lower the burden on the large corona survey. People will be sent weekly questionnaires about whether they had symptoms in the past week, and then questions attached to that. And you will be able to spot your own behavior basically on a map of Belgium, not exactly on your location of the residence, but very close to that, to see what the prevalence is in the Belgian population. Of course, this is again a biased type of assessment, because people need to participate with this. So we will encourage people very much for doing so. What is also, this is observed, what is unobserved and very important to know is the number of infected people as a whole. Some people call this the dark number, something that we do not see, but we want to know exactly, because also a lot of the discussion that has been focused on the first wave against the second wave, and this being different in terms of the underreporting factor. But I will come back to that later. The number of asymptomatic individuals is a very important component belonging to this. And there have been many estimates floating around, but recently Nicola Lau, one of the collaborators within our European project, has developed a live systematic review and established that about 30% of people infected with SARS-CoV-2 is likely asymptomatic. Although she also mentions that there are some issues with some of the papers they have been looking at, and so that care should be taken with interpreting this number. But it's also very important, and I'm going to mention it here because before I forget, basically, is that people that show symptoms are likely to be 3 times as infectious as those people without symptoms. And that's for the first time that we can actually put a number on that. Of course, a lot of uncertainty again, but very important to acknowledge. And then for the number of people, but I will come back to that, I already mentioned health-seeking behavior, but also case definitions have changed the way we look at confirmed cases. And that actually also complicates matters quite a bit, but I'll come back to this. And then we also have transmission events, and what has been very popular in recent decades, I would say, is the use of social contact data. And it's fair to say that this has emerged from a first publication in 1999. There's actually an earlier one in the 70s of the past century. But in 1999, John Edmonds and colleagues wrote a proceedings article about this. And people have been collecting social contact data in different countries. We've been collecting them in Belgium, and we've been using them to model, for instance, in 2009, the influenza pandemic, but also other respiratory infections transmitted through social contacts. Now, there are limitations to using social contact data, but what we've seen, and I will illustrate this in a moment, is that there is a lot of value in them as well. And trying to interpret them in the right way is really a big challenge, but at the same time, it also can give us some idea about which interventions are make sense to fight this SARS-CoV-2 pandemic. In terms of transmission events, I think honestly we are lacking quite a bit of data in Belgium about clusters and where clusters take place and more detailed information about them. A lot of people are putting a lot of effort in collecting more and more information. Countries that experience past pandemics or at least emerging infectious diseases have established frameworks to collect these data in a much better way, and I will come back to that very shortly. But they've been able to establish the risky environments where transmission takes place, and I think that's very important as well. So to limit transmission as much as possible in these risky environments. Of course, 3 dots. I can say a lot more about infectious disease data, and a lot of people have looked at these. And I'm now touching upon 2 books. One is the book by Niels Becker, which he published in 1989. He actually established or published a more recent book, touching upon the same principles that have been available in his book in '89. And his book in '89 already explained that it's quite complex to analyze infectious disease data because of the interdependencies, but also because of the incompleteness of these data. And I already touched upon that with the EM algorithm. And Niels Becker used martingales and martingale theory actually to develop this further. Last year, we were very happy that finally we were able to bring out a book together with UAntwerpen, Philip O'Neill and Jacob Wallinga on infectious disease data analysis. And a lot of the chapters, it's a book about 500 pages with a lot of contributions by people who are now also have been very instrumental in the field of SARS-CoV-2 and epidemic analyses. And we touch upon a lot of things like, for instance, and the analysis of serological data and the issues associated with that. And what both these books, as well as other books, actually cover is very important. In epidemiology here, we're dealing with observational studies. So all the studies we are dealing with are prone to biases, and we need to assess them very carefully. That doesn't mean we shouldn't do these studies, but we need to acknowledge the bias. And of course, there is this very important notion that association is not causation. But that brings us also to the heart of the problem sometimes if we talk to people that then argue that, yes, but this is only an association, this doesn't tell us anything in terms of disease transmission. Well, there are principles to obey to, and then we can get back to very fundamental philosophical issues about conjecture versus refutation. And I very much obey to the principle of conjecture, unless, of course, we can refute some of these things that we are looking at. But the principles are very clear, actually. And a lot of people have challenged those principles in these recent days. And I think that's it often has been very unwise to do so in a public debate. This should be something that's very much obeying to the scientific debate before bringing it out and confusing people with a lot of strange messages, let's say. And I'd like also to refer to the Bradford Hill criteria, which builds, of course, on the work of Robert Koch in expressing a certain confidence in causation or principles that could lead to causation. The Bradford Hill criteria were never about establishing causation, but they were establishing about confidence in this conjecture of causation. And I think this is very much a principle that is spot on nowadays, I think, by Bradford Hill. This is a quote by him, and I'll just read it out loud. All scientific work is incomplete, whether it be observational or experimental. And all scientific work is liable to be upset or modified by advancing knowledge. That does not confer upon us a freedom to ignore the knowledge we already have or to postpone the action that it appears to demand at a given time. And I think that's a very important message that we still should obey to. Let's not overly rush science, but let's use scientific evidence basically to guide us throughout this crisis. Now, let's get to SARS-CoV-2 and the way it also started for me personally and for my group. SARS-CoV-2 is a person-to-person transmission with most likely a zoonotic origin. And you notice that I'm already being very nuanced about this. So it's a respiratory infection. The two features that make it a real threat, as we've observed, is pre-symptomatic transmission and asymptomatic transmission. And human mobility has been one of the key components in the spread of SARS-CoV-2. I've already indicated that COVID-19 can lead to, well, no symptoms at all, mild symptoms or severe symptoms, and that there is substantial mortality. And we still nowadays, we still estimate it to be at least fivefold that of seasonal influenza. Transmission occurs through droplets and aerosol, and there is a lot of discussion nowadays, also in other countries, about which one is the most important one of the two. I think it's very difficult to distinguish between both. I think both make a lot of sense and are consistent with the observations we've made already. And then people are quite eager to believe that fomites are less likely to be a transmission source, although we have to be very careful with that because by increased hand hygiene and so on, we've taken away a lot of exposure. So we have to be quite careful about the fomites, I think. Now, the early work by Jamie Lloyd-Smith has been very clear about this. In ideal circumstances, the virus can really survive for a reasonable amount of time on surfaces. So there is possibility for contamination, nevertheless. The R0 for SARS-CoV-2 has been estimated to be around 2 to 4. For Belgium, and I'll come back to that later, we've estimated it to be 3.4. So the expected number of secondary cases from one introductory case in a completely susceptible population. The estimation of R0, however, is quite complicated, and I'll come back to that in just a moment. And then a few facts, I think. Incubation period, which has been estimated first by Valianyani and colleagues, I think, is about 5 days, mean and median time, 4 to 6 days on average. There is a range, but it has been well established, and I think there's little doubt about that. And the 95th percentile is about 14 days, hence also the quarantine period that was initially set at 14 days and has now been reduced in the meantime. The infectious period is quite uncertain still. People are infectious 3 to 5 days before symptom onset, especially 3 and 2 days before symptom onset, most transmission occurs, and it's believed to last until 5 days after. But there's a huge amount of uncertainty here because this is also measured in ways that are very difficult to understand sometimes. So the first exercise that we've done, and it was actually work that Valianyani, former PhD student of Crystal Faz and myself, has done in collaboration with Jaco Wallinger. We were working on this. We were working on this for bubonic plague, but then we switched gears in January when we visited Jaco in the Netherlands at the University of Leiden, where we were discussing this analysis, and we said, well, let's do this, but let's change that analysis and let's apply it to data that come from Southeast Asia, where they had very good epidemic tree data. So they had transmission tree data, individuals indicating who was their likely source case, and in that way building up a tree with nodes and edges between these nodes. So that was so that we could develop a tree as such. Now, typically a lot of people have used what is called a serial interval, and the serial interval is the time between symptom onset of one individual and its infector. And so that serial interval as such is a good proxy for the generation interval, but you need to take into account that there is a difference between them. And it's especially so in the variability, that's where the difference is. Not so much often enough in terms of the mean estimate, but especially in the variability. And it could lead to an underestimation of the basic reproduction number. And I think this also happened, and people who have addressed this before are actually Tom Britten and Giampaolo Scagliatomba. Now, the issue with these data and with also a publication about these data is that people have over-interpreted the results, and they haven't looked at the detailed nuances in that paper as well. I thought we were very clear on that also in the abstract, but still people believed that 60 to 80% of the transmission occurs before symptoms appear. Well, that's not true. And so we clarified that also because some colleagues at Harvard and so on commented upon our paper to make a few things clear. That these things didn't change the results of our analyses. And also some of these things we just didn't have the data to test. But I think we made that clear, and we're now actually working on a manuscript that shows that there are definitely biases that people have to deal with when estimating generation intervals when intervention measures are in place. And I'm going to go swiftly over the next few slides because I want to tell a few other things, of course. But what I think is very important is that we focus on the generation interval, the time between two consecutive times of infection of one person infecting other persons. And as I indicated already, it's different from the serial interval. And the matching component there is the incubation period that we have to look at very carefully. And so this is what I already mentioned, the work of Britten and Scagliatomba. And what we developed is actually a Bayesian method, building upon work that I've done with Jaco in 2012, and which was also further developed by Dennis Tebees, the colleague of Jaco and so on. And all that code is available for people to use. And at that time, I actually already asked whether we had data from Belgium available for this. And unfortunately, until today, I still don't have data like this for Belgium. And this could be really a game changer in terms of understanding what is happening in Belgium to a larger extent. What did we do with these generation intervals that we've estimated? So it's a distribution we're estimating. And we could estimate the reproduction number, the effective reproduction number, but also the proportion pre-symptomatic infection by looking at which of the generation intervals are in length smaller than the incubation period of the infector. And I'm not going to derive it. There are some diagrams here. There is some notation and so on. But for those who are interested, I really advise you to have a look at the paper. And I'm, of course, available for any questions related to this. The idea was pretty simple, I think. It's working with a latent structure. We ignored the dependence between some of these variables. But that didn't matter for the final result. It did matter, of course, for the statistical analysis as such, and that's something that we're now diving deeper into. What we found was very important. So we also looked at the serial interval, but what we found was that the generation interval and the serial interval was about 5 days in Singapore, about 4 days in Xianyin. And the difference between them could actually partly be explained by the intervention measures, which were much more stringent in Xianyin, in China at that time. Although these the intervention measures in Singapore were also pretty strict. You also see the standard deviation, which is very different from the generation and the serial interval. We did a lot of sensitivity analysis related to this. Again, but the results are not that different. Estimates are a bit different, but the overall results are very similar. And then something that a lot of people have done when you're working with serial intervals, they limited it themselves to serial intervals that were only positive. And that's a big issue, because if you do that, then you're actually assuming that, that pre-symptomatic transmission is not as likely to occur. So you're actually biasing the results of your analysis in that way. And so what we do explicitly is allowing for possible negative serial intervals and allow the data to speak for themselves. And I have to say, initially, we were very much doubtful about whether this should be communicated, because of course this would create a lot of anxiety. But we also found, and it was very important to work with people in Singapore and a Chinese colleague that had some connections in Tianjin to understand these data very well. And it was very clear that there were indeed people reporting to have only been in contact with each other and reporting that the person infected by the first individual actually showed symptoms earlier than the source case, so leading to negative serial intervals. What is the advantage of generation intervals? Well, they can't be negative. And that's an advantage, and that also improves the inference originating from this. So without becoming too technical about this, we also derived a pre-symptomatic transmission. And also there we did the sensitivity analysis for allowing all serial intervals, if they are not well known, to be negative. And it did have an impact on the proportion symptomatic. And that's the P column here, the fourth column, where you see that the substantial proportion of this transmission occurred pre-symptomatically. Again, I would like to stress it's very important to take into account that we were dealing with a situation where a lot of intervention measures were already in place. And this is also seen in the the effective reproduction number we've estimated based on these estimates of the generation interval. And whereas we know it's between 2 and 4 for SARS-CoV-2, we've estimated it here for the curves that we've seen in Tianjin and in Singapore to be around 1.1, 1.2, a little bit higher, up to 1.6, depending on where you're looking. And the take-home message is here that if these intervention measures would not have been installed, we would have seen reproduction numbers close to between 2 and 4, but we also would have seen that this proportion symptomatic transmission would be more in the neighborhood of 20%. So that's important, of course, to know and to realize that it's not 60%, but it's more in the direction of 20%, as also our colleagues from the London School of Hygiene and Tropical Medicine have shown. There are many limitations to this study. I will not go into detail. We are dealing with all of them, basically. Some have some more priority nowadays than others. But the essential take-home message is contact tracing is truly very important. And collecting the contextual information is also especially important. And of course, the conclusion for fighting this pandemic is that we should really acknowledge pre-symptomatic transmission, and measures such as social distancing are tremendously important from controlling the spread. I think that's fairly well known nowadays, but at that time, of course, this was really instrumental to know. Our work has been picked up quite a bit, also internationally in the media and so on. In Belgium, it was not picked up very quickly. I think partly because it's of course, with all these nuances, very hard to understand. But the take-home message was eventually was picked up. Now, let me go back to the Belgian COVID-19 pandemic, and I'll focus on the highlights again. So I think we are all aware that it truly started with many importation from northern Italy and elsewhere at the end of the spring holidays, around the 25th of February. But several people, including Piet Maas and the colleagues like us and the Bozere, who looked at over mortality, already indicate or now indicate that they've really seen that there was transmission before that period, but the extent of the transmission was really picked up at the end of the spring holidays. And of course, basically Belgium was not ready for this, as many other countries were not ready for this, and eventually a lockdown was installed. It's fair to say that the lockdown that we experienced in Belgium was different from the lockdowns in other countries, less stringent, let's say, but still quite important that, yeah, we had an efficient lockdown in the sense from the epidemic point of view, that it really curbed the curve. And I've been working with, amongst others, with Matthias, with Marius and others within the GES group to formulate some of these exit scenarios where we tried to allow as much as possible to open up society again, but then thinking about, how should we structure that? What are the contexts that are possible? Is business to business, opening up business to business, business to customers, and so on? Is that all possible? What are the measures that need to be instated, and so on? A huge amount of work, and for those who haven't done so, to understand that better, I would really advise you to read our GES reports. Also, they are very limited in the sense that a lot of more work has been done to feed into these reports. And one of the things that we developed are mathematical models to investigate this further. And these mathematical models have not been put into a GES report for various reasons. One of the reasons being that it would bring a very disturbing picture towards the politicians who should interpret this in the right context, I think. So Marius spent a lot of time developing a very simple methods to try to picture how this pandemic was evolving at that time. And we had a color scheme in terms of the number of new hospitalizations, which actually guided us in this exit strategy, where we defined different colors for different phases in this exit strategy. And it's very much related to what we nowadays talk about in terms of the barometer, which is currently being developed. Now, what are the principles that we have taken into account? Of course, is exponential growth is by definition the case when a reproduction number is larger than 1. Some people have talked about sub-exponential growth, of linear growth, and so on. But the basic principle is really sub-exponential growth, and we'll come back to that later. Exponential growth is the default. Sub-exponential growth is there because there is, for instance, spatial heterogeneity. But again, I can come back to that later if people are interested in that. So the bottom line is, without interventions, epidemic spread cannot be mitigated unless there is depletion of susceptibles. And what is very clear is our lack of understanding of how the immunity really works against SARS-CoV-2 makes it very difficult to trust going for or striving for immunity. Sweden has at some point in time expressed their willingness to go for that, but they also came back from this, and many countries in the world think are not going for this. And I think that's a wise decision, but we can go on that in the discussion maybe. Heterogeneity is key, and I think it's still an ongoing scientific debate also about the herd immunity threshold. And there's been people arguing that we need to reach 60 to 70% of immunity to reach that herd immunity threshold. So maybe for those who are new to the concept, the herd immunity threshold is the threshold or the number of people or the percentage of people that need to get immunized for the virus to stop spreading in a population. So the 60-70%, that's actually what we try to go for, or should try to go for, but it could be that we're underestimating the heterogeneity, and then some people, and I think Gabriela Gomez has been pushing this to the very low end. Let's say if you can reach 20%, then we're already hitting herd immunity. I think she's right in some of the points that she makes, but there has been a Twitter discussion even about that with Mark Lipschitz, and Mark Lipschitz is also right. So there's none of the two are wrong in that sense, but I think this is a lively debate of what a debate really should be amongst scientists. What is also very important, and especially for people to understand, is that chance events hinder perfect prediction. And so a lot of people say you can't predict this and all your predictions were wrong and so on and so on. A lot of people asked me in the initial phase, when do you think the peak of this epidemic will take place? And I've never answered that question really, because it all depends on our behavior, especially with SARS-CoV-2. And the reason why I also didn't answer that is because of the self-defeating prophecy, or what is called as the prophet's dilemma, is the prevention paradox, some people call it, is that if you cast the warning message that things grow exponentially, then people will adapt their behavior, hopefully at least, and that's what we've seen in the past, and then that will curb the curve, basically. So you'll see our predictions being false, and yeah, a lot of people will then say in hindsight, well, these strong measures that were instated are actually not necessary. That's of course the wrong interpretation. And what we do with our models is we do not aim for prediction. We aim for better understanding and looking at possible scenarios given certain behavior. And then of course the proof is out there, and we need to validate the models that we develop and the things that we do in terms of all the data sources and information that we collect. And this is partly what we've done. So where are we now today? If we look at this panel, and this is taken from the Cienzano report of today, what you see in the upper left panel is the number of confirmed cases, and a lot of discussion has already gone into this. But the underreporting factor that we've estimated, but again with a lot of uncertainty, in this first wave was 1 to 38. In the wave in August, we believe it's 1 to 5, but again, levels of uncertainty, of course. And now I think, I'm not sure. Today it's very difficult to estimate this. Also because we cannot disentangle between, for instance, people returning from holidays, travel behavior, what is the impact of contact tracing and so on. So it's quite complicated to really understand this very well. So a lot of people try to look at new hospitalizations as a better or an alternative to this number of confirmed cases. Some people would like to look at people in the ICU, and some people would like to look at mortality as such. The problem with these last three indicators is that they're always delayed. And we're always too late, basically, if we want to intervene from an epidemiological point of view and also from other points of view. It is smarter to intervene earlier, because the later you intervene, the more severe this intervention needs to be to get back on track to a low number of cases, low number of hospitalizations, ICU uptake, and deaths. And at the very end, I will come back to the projections that we've made, the 5-day projections, based on the evolutions that we've seen in the recent days. And indeed, they are very worrisome, as already mentioned in the media. So, yeah, the differences in case definitions has really made this underreporting factor go down. I think it's a bit up again because of these issues that I mentioned. But this is something that we really need to acknowledge, need to take into account. And for me, the question, which indicator to choose, is actually the wrong question. You need to look at all these indicators, but of course, some people will say, I need to look at the hospitalizations because they are really expressing the burden of disease, whereas the lead time is actually really given by the daily cases data. And I think it's very important to acknowledge that. So looking at the hospitalizations is actually too late to intervene with lighter measures. And I think that's a very important point to make. Yes, of course, there's also the issue that more testing has been going on, although recently is the opposite, and there are some delays now. It's also very clear from the data that Cienzano is publishing, that there are delays in the data that in the number of confirmed cases. And instead of 3 days to wait until we see confirmation, I think we're almost up to 5 days which is a lot actually to really know what's going on. Another aspect is that hospitalization data as such, it could be nice to look at in conjunction with other data sources, but it's not being shared by all countries. So if you want to look at international rankings, we're doing a poor job because the number of confirmed cases is very high. And of course, this has implications not only in terms of the epidemic spread as such, but also on how other countries perceive us, our country, as being a bad student or a good student in the class. And that has economical implications. But now I'm going into in an area where Matthias is much more the expert than I am. So I'm not going to go into that, but I think it's an important point to make nevertheless. I'm not going to go and talk about speed and acceleration except for this slide. I want to focus, and this is not as up to date as possible. I want to focus on the third column. And in that third column, the reproduction number is calculated based on the cases and on the hospitalizations. And what you see is that qualitatively, these two reproduction numbers are the same. They show the same behavior. And if you look more carefully quantitatively, what it shows is that the cases data give you indeed a lead time. So the reproduction number for the cases is earlier, or shows what will happen later in the hospitalizations. So stressing again this very important comment that we should not only look at the number of cases and the number of hospitalizations, but also on the acceleration, which is very important. And then the principle is, of course, we need to keep our curve as low as possible. This is the smartest thing to do, not only from an epidemiological point of view, but the effort to maintain a curve, whether it's high or low, is the same, especially from our social contact behavior, the way we go about things and so on. But the effort for contact tracing and other things is, of course, way higher when you are high up already, because you have to follow more people. This should be more intense, and we know from the first line, and as well as from the hospitalizations, that other care is under pressure nowadays. So that's very, very important to take with us. I'm having a look at the time that I still have, so I'm going to make a few comments on a few issues, be very short about that. The slides are available for everyone who's interested, and I'm happy to take questions later on for specific items. Highlighting a few things, studying the effective reproduction number is very important, because it can tell us whether and at this moment in time especially, the non-pharmaceutical interventions are working. To some extent, because again, it's association, not causation, but of course, there are some epidemiological principles that really show us that this is the important bit to do. Now, some people always ask, can you really look at this being the cause of that and so on, as certain intervention measures have worked? What does that mean? Well, it's very important to say that it's not the moment when these intervention measures have been communicated after a National Security Council that is important. It's already important what is communicated before. And it's my gut feeling that what it comes in the media is very important. And so the messages in the media should be very, very well thought through from both sides, being too alarmistic, but also being on the other side, minimizing the problem. And one illustration of that is actually during the lockdown, before the lockdown really took place, people 65 years and older already changed their behavior. And this has been shown by the last physical contact that those people had at that time. That was before these more stringent measures were announced. People between the age group 18-65 years have obeyed very much to that, to what the National Security Council announced, but then the 0 to 17-year-olds took a longer time still. So here you also see it's very important to communicate to different groups in different ways. What we're doing now is having the dance, let's say, the hammer and the dance, and I think this should be communicated much more clearly. This is the thing that we're doing. We're trying to keep the R low, or that should be our goal, although maybe that's not what everyone is convinced of. But from an epidemiological point of view, this makes a lot of sense. And again, also from other points of view. I won't have too much time to go into this, but we have been collecting social contact data. And I just want to illustrate this with this slide, where we have been questioning people about the number of contacts that they made. And what you see here is over the period from the lockdown until the beginning of August. And at a certain point coming out of the lockdown, you see the number of contacts really increased in the 18 to 29 years of age group, 30 to 39 a bit. And then for the others, so the most dominant increase we've seen for 18 to 29, a little bit less so for the others. But what you also see is at the very end, wave number 8 was actually a decrease in the number of contacts. And that was because of the National Security Council with the more stringent measures in August. And it's no surprise really that this was truly, was a translation into, in the confirmed cases. This is what we've seen. And these are contact matrices and so on. These are actually also available online, so you can actually look at that. But these contact matrices actually fit what we see in the age distribution of the number of cases. And that's also what we use in our mathematical models. Now, there are other questions asked in these contact services. And here is the website where you can actually play around with these. We're still working on the comics data to make them available, but I should be able to give a clear go at the end of the day. And then this also will be available for others to use and to play with, let's say. We will be conducting new contact surveys very soon. And maybe very important, contact patterns are very different in different regions of the world. And in panel A, what you see is there what would happen for influenza in terms of the transmission potential. On the bottom, you see what would happen for SARS-CoV-2, because we believe indeed children from 0 to 10-year-olds at least are less susceptible to infection. And if you look very carefully, Belgium is red here. So there are different reasons in Belgium to believe that we are actually much more socially active than other countries are. And that's why we see differences based on social contact data as analyzed by Hilton and Matt Keating. The Zero survey, I'm going to skip. We have developed several mathematical models. I will not go into them. They're available for everyone to look at. The code is also to be shared, so we're very open about things. And the results of that is the basic reproduction number being 3.4, the lockdown pushing that reproduction number below 1. We've estimated it to be 0.73, which is actually fairly low. So it was a big achievement. And nowadays, of course, we're above there, and I would like to end. So there are some dark number estimates, but I would like to end with where are we now? So these are the predictions for the next 5 days. We are very reluctant in predicting further. This is the number of new cases. And what this prediction assumes is that there was no change in behavior. So we're all hoping that people are changing their behavior and that some of these scenarios that we see here will not take place. And do note that the numbers on the y-axis are different for the different provinces. So it's quite problematic in Brussels, as you, I think, are aware of. But also Antwerp and Liège are coming up quite quickly. For the number of hospitalizations, it's still quite different. But we do know that there is a delay. So we hope that we can curb the curve before truly bad things happen. But this is still very worrisome, of course. And also you see what is predicted for Liège and for Brussels. As always, we hope that these very negative predictions are not true. And then some people like to focus on the positivity rate because of the comment that lots of people have made about the numbers of testing going up. Well, this is the picture for Belgium, but it actually doesn't give you the best picture. If we look at Brussels, this is a bit more worrisome, where we see that the positivity rate is truly going up. in different age classes, and especially what is worrisome is starting to grow up very quickly in the 41 to 60-year-old age group, 61 to 80 and 81 plus. And of course, that's where the burden is. So mostly, not only there, of course. So I would like to thank you. I'll stop here and thank all the collaborators, and there are only a few shown here, but I'm happy to take any questions you might have.
Yeah, thanks a lot, Niels. With Matthias here. So sorry that I came late, but of course I had heard some of this earlier in September in a conference we organized, but I'm sure everybody is very impressed by what you have shown. Let me just reiterate. I think Michel has said that in introduction. This work is not only scientifically excellent, it is also hugely useful. This has been the backbone of our thinking in the Gs, and is still now extremely influential in the various C-level discussions. I think that indeed, what's really impressive is how you are able to rely on a number of methodologies in order to put all this in models and be able to indeed have assessment. Now, you hear people saying, look, okay, virology and the like, even though some of them exaggerate, especially with their tweets and the like, our friend Mark van Hans and others. But at least, this is a medical science, and we understand that. The modeling, some people are kind of more skeptical, do we agree with all these assumptions and all that? Now, of course, my standard answer to these kind of things is, economic models are often used by many important people, the European Central Bank, the OECD, the IMF, and so on. And let me tell you, from what I can see, epidemiological models are much more convincing. Of course, they are not perfect, but the way you manage to have all this data is extremely impressive. And I think you have conveyed that in your talk here. And as I say, very often in our discussion, we have an idea, and then what can Niels' army tell us about? Huh? So that's really so it has been, as I say, because everybody has a model in their own head, and it's important to put it on paper and see, because indeed a model is telling you what a set of assumptions deliver, and then you can talk about the assumptions. And I think that has been great. So I have a number of questions, but I think it is probably better to first ask the audience, and I think Hilde can read out the various questions and ask some of her own. And then I'll come back a bit later on, trying to ask a couple of others that have not been asked. So Hilde.
Thank you, Professor HENS, for this wonderful talk. The first question is a question from Roland Pochet, who is the president of the Belgian Brain Council. COVID-19 reaches the brain. Are brain symptoms observed, studied? Are they considered as mild or severe symptoms?
They're studied. I haven't been involved in the study of what it does to the brain. And the problem, I think, nowadays is that it's not well known what percentage of the population, of what percentage of people infected with COVID-19 really has these issues. And the question is also related whether or not that is severe. There has been anecdotal information about the severity of this, but to what extent is it severe, and what is the percentage of that? Because this is not unique only for SARS-CoV-2. Other infections have this as well, but to a lesser extent, I believe. But now it's getting into the media, and then it's often difficult to grasp how representative this is. So I don't have a full answer to this, but I think it would be really instrumental to have much more information about this. And it actually relates also to the long COVID, the long haulers, people that experience COVID and difficulties after COVID infection for a very long time. I've been talking to a few people say this is really problematic, but at the same time, they also acknowledge that there are some people that claim this to be due to COVID, but it's actually not. It's due to other reasons, but they now finally are getting a stand basically, and they can speak up to express their worries and concerns. Yeah.
Then a second question is from Ton Lienert. What is the state of the art of adding behavior dynamics in epidemiological models? And are there good recent papers on this?
Yeah, I think a lot of the papers that work with SARS-CoV-2 are already dealing with this. I think especially, it's not because they're in our consortium, but the group of the London School has done a huge amount of work in this aspect. But honestly, I think also we lack quite a bit of that behavioral epidemiology bit. And I've been saying this for a few years already, that behavioral epidemiology is really the future. Well, the pandemic came a little bit too early in terms of the research and the state that we are in. Some people have been looking at this from a more theoretical side of things. I'm thinking about Alberto Nofrio, Piero Manfredi. We have been setting up a study to look at contact patterns in chronically ill people, because behavior there is very difficult to understand, and it's also different from the average population, and the average population which doesn't exist, but anyway. And then the other thing, and I think that's something that the Swedish example has shown to some extent, and actually I think we're seeing the same thing in Belgium. If numbers go up, people are more reluctant in exposing themselves to risk. And some people are very anxious even. And there are models that can be constructed that feed into that, that say, well, if the numbers go up, my transmission parameter actually decreases because of that. And they've been shown to fit these data fairly well. And I think that's the Swedish example is one of them. If numbers truly go up, then you see, and I've been talking to Tom Britton, for instance, at Stockholm University, who says like, yeah, we've seen this. People are not visiting each other anymore and so on. They automatically, almost without the government telling them, have refrained from making contacts. So there is some work, but a lot more needs to be done still.
Okay, then an interesting question from Dr. Michel de Wilde. What is the relation between vaccine efficacy and herd immunity thresholds?
Yeah, well, the herd immunity threshold I'm talking about or referring to, and when I talk about 60 and 70% is herd immunity threshold against susceptibility. So people need to be 100% effectively vaccinated. Of course, a vaccine is never 100% effective. So people have been investigating that a 70% efficacious vaccine, which is administered very carefully, could be successful in curbing the curve, basically, in getting to this herd immunity. But what they haven't mentioned, and it's mind-boggling, is what coverage do you need to reach that, and in which groups do you need that to reach that coverage? So that's something that still needs to be investigated. So we are getting ready to do that in the same way as we've done in the past for influenza, for instance, where we looked at more than 5,000 different vaccine schedules, taking all of that into account. The problem here is it will be even more complicated because you have to take behavioral change into account. Because what we will see as soon as the vaccine is there, the perception that people can return to normal life. And that will be fairly complicated. So we will do the full thing in terms of as soon as we have first vaccine efficacy estimates, and then play with the percentages, play with which groups need to be vaccinated and so on. So happy to do 5,000 simulate. Well, it's a supercomputer that does that, so that's not a problem. But it will sharpen our idea in who that we need to get the vaccine to first. And then, of course, what is also very important to take with us is it's not only vaccine efficacy against susceptibility, it's also vaccine efficacy against disease. So, and infectiousness. And maybe that also can help to decide whom to vaccinate. If you can develop a vaccine that doesn't work well in 65 plus, then maybe you should focus on stopping the transmission and vaccinating those people that come into contact with 65 plus. So I think, and also the Superior Health Council has advised that we should focus on the vulnerable groups and on healthcare workers. I completely agree with that. But we need to see that confirmed in the vaccine efficacy results that we will see, because otherwise we would maybe be making the wrong decision at some point. So we should be open to things, but at the same time, I know some philosophers and psychologists are now claiming that you should actually vaccinate young people first, which I don't think is true without the evidence. So let's wait for the evidence to see what is possible. Yeah.
Okay, and then also a question of Olivier van den Berg, who is a microbiologist at ULB, thanking you for your excellent talk. And according to your Belgian model, what would be the impact of the massive use of less sensitive tests, such as antigen testing, as recently proposed by Michael Mina in the New England Journal of Medicine? And thank you again from him.
Okay, well, thank you very much for that question. Spot on, I would say. There is a preprint that will show up hopefully today or tomorrow on medRxiv. First author Peter Levin, where we looked at universal testing. Now, we looked at PCR testing. We know PCR testing has its own issues. Think about the residual RNA and so on that is being discovered. And yeah, there is some discussions about that. But I believe very much in what Michael Mina is actually putting forward. These tests are less sensitive in my understanding, and but they are able to capture the super spreaders much earlier. So whereas they are less sensitive, there is certain value in getting these tests rolled out and basically used. But you should use them at high frequency every 2 to 3 days. So that's a very high frequency. They're not costly at all. In thinking in terms of budgets of it, $1, I think it was, or something. So if that could be really rolled out quite quickly, then maybe it's a good option. At the same time, I think, like always, it's not the only solution. We always have to use different solutions altogether. But I very much believe in this being a potential solution. The only problem with this is also, again, if people use these rapid tests, they could get a false impression that they are safe. And from an epidemiological point of view, it does make sense to use these tests. But from the individual point of view and how this is conveyed and so on, it's maybe problematic. But universal testing as such could potentially work, but there are a lot of logistical constraints, I would say.
Okay, and then Michel, you had a question too?
Yes, perhaps I will start first with a comment. You know, I think one of our main challenges today is to restore the trust in the public. And I really think that the type of approach and the talk that we hear today are really essential to restore this trust. I think that the way we explain things, as Neil did, and to show that what we do as experts, as scientists, is really based on the best science, is extremely important. And I must say that some of the slides that we were seeing today are extremely important. And I think that they are much more, I would say, they give much precise information than the numbers that we received every day. Having said that, I have two related questions to Neil. First, in your models, I don't see really, but perhaps I miss it, the important observation that, as you just referred to, super spreading events are critical to explain. And I think that, for example, when we talk about the R values and all these things, I'm wondering whether, you know, super spreading events and super spreaders are enough considered, knowing that probably only 20% of the infected people effectively transmit the virus. And the related question relates to the validity of models. I think that in the reasoning, and you mentioned this again, that models depend on the way people will follow the rules that are imposed, the non-pharmaceutical measures. So now you refer to vaccines, but what about other interventions? And this is something on which with others, Michel Kazachkin and other scientists, we draw attention. There are still treatment, including antiviral treatments, such as those monoclonal antibodies that might come soon. And do you include in your reasoning the fact that indeed those pharmaceutical interventions might indeed help? And I think it's important also to indicate that they will not replace but be complementary to non-pharmaceutical measures and of course vaccines. Thank you.
Okay, thank you, Michel. Thank you also for the comment, and I think indeed we never really got the opportunity to get a forum for this to the wider audience on national media and so on. It's too complicated for them, they often argue. But I leave that to the public to decide, basically, so I would not preempt that discussion. Some things can be explained in more detail and should be explained in more detail. And even if people do not understand it, what they should know is that there is much more behind some numbers and the advice that is given. So I very much relate to that. And that's why I also try to share slides and so on. And I could spend more time in doing so, but there are only 24 hours in a day. So that's one issue. And thanks also for the question on super spreading. I think this is tremendously important. So when we started our modeling exercises, we've started from the models that we had available to us. We had a metapopulation model that we developed in collaboration with Vittoria Colizza. We had, next to that metapopulation model, an agent-based model, which is called STRIDE, that we developed for measles, for influenza, and so on. And then we had, and that's something we developed from scratch, a stochastic age structure transmission model. We use 3 models because all of their pros and cons, and I think that's very important. But what was not in there in none of these models was super spreading. So one of my PhD students is now incorporating that. The super spreading item is incorporated in the agent-based model. For now, we are incorporating it in terms of the number of contacts people make, but we are also incorporating it in terms of the infectiousness of each individual, in terms of the ability, even when making contacts, to infect many people at once. We are also looking a little bit more theoretical from a statistical point of view to over-dispersion, and I'm referring back to the work of Jamie Lloyd-Smith in his Nature paper in 2005. We're revisiting that work with other models, statistical models then, as an ingredient to feed into that. Following also the work of Alan Brooks Pollock. And it's actually building a little bit upon a discussion I had with her at one of the ECDC meetings last year. So yes, we are doing that exactly for the reason that you're indicating, is that if we can prevent, and we need to know more about super spreading, of course, but if we could actually look at super spreading in much more detail, then some of the measures that we have nowadays, which are really stringent, can be loosened a bit further, and other measures maybe have to be enforced. Let's think about the disco and the nightlife and so on. We're not allowing that because we've seen in Southeast Asia that this is really a tremendous opportunity for super spreading events. And I think we need to gain more knowledge to actually have a more finer detailed approach to that. But at the same time, the disease dynamics are really different when super spreading comes along. And so that's truly important. For the antiviral treatment, we published a paper, Torneri et al. In BMC Medicine with Johan Nijts, where Johan Nijts, I think you know, is also really much focused on having these antiviral components ready, basically, to deploy at the start of a pandemic. And we've shown that if these things would be available, then we could have stopped this pandemic quite drastically, quite soon. This was a very simple toy model. So we're developing this model further in this striped agent-based model. And we're going to continue to do that, to be ready for the next pandemic, let's say. Because I think it's really truly instrumental that we prepare ourselves in a much better way. And a model which has 11 million Belgian people in it, which we can further develop, and we invite everyone to contribute basically. I think it's necessary to also to sharpen these questions again and to think of the best way forward to tackle this.
Thank you very much.
Hello, good afternoon. Thank you very much for your very interesting presentation. I would like to ask two main questions. So one is also following up a bit on what Michel just asked, which is related to the trust that citizens might have in everything that has been done to combat this pandemic. So as you mentioned during your presentation, the contact tracing apps are crucial and they might be very important to contain the pandemic. There have been, however, many concerns regarding privacy and how exactly this data is going to be used afterwards, which in a way reminds a bit all this kind of anti-vax movements and the role of trust and also on the information. So I was wondering if there is some kind of way that we can assure users that they can really trust on these apps and that is also on their best interests, and if they can be confident about how our data is being used. And I'm not sure if I can already ask the other one, but it's well related to what you also mentioned, that if we want to have a clear kind of idea of how the pandemic is evolving, looking at hospitalizations might not be the best way, because as you also explained, there's a kind of a delay. And the looking at testing and the number of cases is more reliable. You also did mention that currently there are higher delays in obtaining the testing results. And I was actually wondering what is driving this delay? Because, in a way it would seem that since the pandemic is already going on for a while, this testing would become even faster instead of the other way around. Thank you very much.
Okay. And thank you for these questions, Sophia. First of all, for the app, privacy has been a huge concern for the app as such. But I think, and that's something that we haven't done well in Belgium, the app as such could have been there much, much faster. If only we would have connected to the right people in the other countries. And I think Marcel Salaté being one of them, Marcel Salaté has been communicating about an app in a way which I think builds trust. And so this goes hand in hand, communication and an app, and to tell people what the app can and can't do. Because for me, the app is not the only thing that will solve it all. It's one of the many things that we have to combine to fight this pandemic. But yeah, the privacy issue with an app, there is always an issue of privacy. And one of the reasons, for instance, testing and tracing has been put at the mutualities was exactly that, because there would be more trust in that system. I'm not sure whether honestly those people that don't trust it and they feel that their privacy is breached, let's say, will be convinced by those arguments. I don't think that's true. So I'm looking at the gray zone of people that are a little bit in doubt. Why can I install the app or not? And what I haven't seen on the media or anywhere else is to explain how this privacy is actually dealt with. What is being done exactly? There are diagrams and you can simplify them because some are very complicated, but you can really simplify them and saying, this is where the information goes, this is what people see, and this is actually, yeah, when the data will be after 14 days will be excluded from the list, and so on and so on. So I think communication there is really key. Just for your information, we have been working on an app with people in Ghent, but yeah, this was already ready in June. So it's been quite amazing of how things have been very slow at first. And I think the big lesson learned is, and I hope we learn this lesson during this crisis, is that next time all of this needs to be in place. There needs to be one line of command, and all these vehicles and topics should be in a manual, basically ready to be deployed as quickly as possible. In terms of the delay in testing results, it's an observation I make in the sense that, well, now we're above 3,000 per day, 3,175 or something, if I recall well. I just looked at the numbers this morning, but and that number of the 3,000, it's not from today, it's from last week. So it's amazing that a big number like that is only coming in right now. And earlier on, we could model this. We have modeled this we've done some work in 2013, where you can work on delay patterns and so on, and you can really model the percentage of delay. If you would repeat that today, we haven't done so, but I'm very sure if you would repeat that today, then we would see a big delay. Now, where's this delay coming from? I think because our first line is being flooded, basically, by people that want to get tested. Also because of schools reopening and small children having rhinovirus, more than anything else, they are being tested now, just to be sure that it's not corona. So has been an abundance in testing, and some of the laboratories just can't cope because they don't have the people to cope with it. So they are trying to work on this to improve this again, but the numbers have been coming in much more slowly than we have hoped for. And I think, yeah, Matthias knows a lot about the testing because he has been one of these working groups. It's really tremendously difficult to get everyone on the same page, I think, and also to minimize delays in getting test results to people. When I and my family returned from an orange zone, it took 4 or 5 days to get test results, and we even didn't get them all at the same day. And that was only in August. And I think in the recent times, what worries me a lot is that the numbers even the numbers that are so-called confirmed or validated are still not complete. So I'll leave it at that, but happy to answer any follow-up question.
Well, thanks a lot, Niels. I think on numbers of questions, I think one problem is that we are reaching our time limit, 2 o'clock. We still have 1 or 2 minutes ahead of that. I just want to conclude a little bit by saying that first of all, I'm sure everybody has been very impressed by not only what you have shown, but also the breadth of the answer, showing that you are not only a biostatistician, but you have quite a view of the whole epidemic and the interdisciplinarities. So you are, our institute is trying to be interdisciplinary, and therefore I think you're a great speaker for our series. Now, as an economist, when trying to think about your kind of models and our kind of models, typically economists, what they like to do, and I've pushed a bit for that in our discussions among experts, is to say, first let's define our objective and then see how we can achieve it. Because economics started by asking, what about the people having wants that are in excess of their means, and how can they allocate their resources in order to achieve the best for themselves? So here you could ask, okay, what kind of measures do we want to implement in order to achieve a given objective? And a given objective, there is, of course, we would all love to go back to pre-COVID times where we have no virus and where we have no restrictions. You put 50,000 people in the Roi Baudouin Stadium, and if nobody is infected when getting in, nobody is infected when getting out. So that's you know, the pre-COVID dream. Of course, we are not in that level, but I think one element which was very important with what you said is that the efforts in order to go down a particular contamination level are in a sense independent of where you start, kind of. So I think this idea that somehow it would make sense to make an effort now in order to be really at a lower level for quite some time. Now, it's not that easy because you always have people entering the country and all these kind of things. And so there is a problem of coordination around Europe. But I think this idea, and I don't know how easy it would be to say, look, you know, in our model, this is where we want to be at this time. And these are portfolios of measures that you would want to follow. And here are the choices for you politicians to make. I think we are unfortunately not there yet, even though I like the barometer and all these kind of things, but we are still quite far away from that. Then on top of that, coming to Michel's question about the R and the super spreaders, you know, economists are often criticized for having representative agent models. So let's assume that everybody is the same and just one person, and let's try and do this kind of dynamic optimization. Now, this is in a sense, the R has a bit of the same criticism. You know, it's an average, and you know, the average doesn't say much if indeed most of the contamination is by a couple of super spreaders. So I don't know to what extent your models can deal with both these things. But you know, if I had a wish list, this is what I would want to do. Because I think, you know, as you said, in March, Belgium was not ready to face the virus. Well, you were much more ready to help us analyze it than others. But, you know, for the next one, I would like you to be able to do this kind of thing, this dynamic optimization with the portfolios of measures, plus a proper integration, you know, it's a wish list, a proper integration of heterogeneity within the population. Yeah. But, you know, anyway, so I don't know what your reactions are to this, but beyond the fact that more research is needed, which I'm sure is one of the answers.
Well, actually two things. The contact budget thing that I've used as a term on the national conference and which has lived its own life in the media, which I'm a little bit uncomfortable with actually. I think it's an exercise I would very much love to do. Because I think, as I've said many times to you, to others, but maybe also to everyone here, I believe we have options. We have options to get through this epidemic without locking down everything. And that's actually what this optimization should be about. And matching the heterogeneity as well in the population, saying what is possible for this group is maybe not possible for that other group in terms of their willingness and their psychological state of mind to cope with this. So yes, I'm very much in favor. There has been a small exercise by colleagues in Melbourne doing this, but no surprise there, sorry. You didn't need a model for that, so no offense to these people. But I still have to talk to them because I think they've done what I think is much more interesting thing as well. They focused on the infection fatality rate and then looked at who can make contacts and who can't. And the obvious result is, of course, if you lock down 50 plus, you're there. It's okay. Everyone else can go at large and do what they want, which is theoretically, yeah, that's okay. But in practice, that's much more complicated. So that's a no-go to some extent. I want to look at this from a different point of view, where there is more possible between generations as well, because people need it basically. I have a lot of people that say, I can't, if I can't see my grandchildren for the next few months, then yeah, forget about it. So we need to balance that. So that's definitely necessary. I think we have quite a few ingredients to make this happen, but we don't have the granularity that I really want to go for. And that's related to your second question. So, so the agent-based model we're now further developing with super spreading, people get their individual reproduction number. Basically, that's actually what we're assigning to people, but we disentangle that in terms of contact behavior and in terms of infectiousness. And so they play along, of course. If somebody is very infectious but doesn't meet any person, well, too bad. I mean, that person is not going to be a super spreader. So I think you need to actually do both of them, and then to see, and that's what we really should have, is a good representative cohort that we can question and really ask for, are you following the rules or not? And they're really filling in this trust in the most trustworthy way, so that we can take that into account. And then we can see what things work and what are the things that do not work. But we need much more information to feed into a system like that. And we're actually now, the reason, one of the reasons that Peter Libin, who was working with Anne Ween in artificial intelligence, is now at Hasselt, also working still with Anne, with Philippe Lemay in Leuven as well, is exactly because we want to learn with artificial intelligence what is possible. It's a little bit mind-boggling because we have to translate between computer science, mathematics, and epidemiology. But I think this is basically what the future should be about, trying to get more disciplines into this game, basically. And I think also psychology and all that we learn from people's behavior now. So one of the crucial things that I think is sometimes lacking is the urgency with which we have to collect specific data during this crisis, because it will inform so much of what is going to happen or what can happen for the next one. And that's a little bit pity. It's a pity to see that this has to come from almost, and it's a good thing, from academia, but that a government should buy in on this much more, I think, as well, to collect these specific data for these specific topics as well. And they should really support this much more than currently is the case, I think.
Okay, thank you. Thanks a lot. I think we are over time, so we need to. It's not your fault; it's my fault. So we should stop here. But I think we should thank you again for a great talk, and I want to thank you personally also for all you're doing for our country. So thanks a lot.
Thank you, Matthias.
So,
thanks,
and thanks to everybody and for the questions, and Michelle, who took over the introduction from me because I was late. So it was wonderful. Thank you.
Thank you to all. And perhaps a last point, if you have other questions that you would like to discuss with Niels or with us, don't hesitate to send them to Anna Wozniak, who invited you to attend this seminar. Thank you very much.